described what is a group and then what is a field. So we now move on to a very important problem in cryptography called the discrete logarithm problem. Just like the factorization problem is very hard, this is another problem that is very hard and upon which the security of several signature algorithms depends. This is the discrete log problem. We will define the problem and then we look at various applications of this. So let P be a prime number and let G be a primitive root of P. So just think of the set 1, 2, 3, 4 up to P minus 1 and just let's think of so this thing was going to be a group. That's the set 1, 2, 3 up to P minus 1 with the operation multiplication modulo P. So this is the set and this is the group, and let G be a generator of this group. So let me just define what is a generator. A generator is an element of the group which can generate all the other elements by performing that operation repeatedly on itself. So let's take an example of this. So let's consider the group Z7 star with the operation multiplication modulo 7. The elements of this group are now let's take some arbitrary element, let's say 2. So I start with 2, then I go on to 2 star 2, then I go on to 2 star 2 star 2 and so on. And I ask myself the question, have I generated all of these elements in the process? So the first element was just 2, the second element is 4, the next element is 2, 4, 8 and multiply these three things modulo 7 and I get 1. So I find that 2 is not a generator because now when I find a number repeated over here and this number will keep repeating. So this is not a generator of this group. Let's try 3. Nine is the same thing as 2. I'm sorry. So this is, the next one is 6 multiplied by 3, so that's 18 mod 7. So do I get all the elements over here? I get the element 3, I get the element 2, 3 3s are 9, which is 2, then 2 3s are 6, 6 3s are 18, mod 7, that is 4, 4 3s are 12, mod 7, that is 5, 5 3s are 15, mod 7, I get 1. So I see that I get all the elements in this case, so 3 happens to be a generator while 2 is not a generator. So I am really referring now to elements of this type. So first and foremost, in Diffie-Hellman, I need to define the group, something like this, and I need to define a generator. So this thing is a parameter of Diffie-Hellman, what we call P. So I am really looking for groups like this, where P is a prime number, so that's the first parameter. And then I'm looking for the next parameter, which is G, a generator in this group. An example of a generator is 3. Okay, so with that background, let us look at how Diffie-Hellman works. So let P be a prime number and let G be a generator in this group. So what that means is G, then G star G mod P, G star G mod P, and so on and so forth. So do this 3 times, do this 4 times, and so on, and you will soon see that you get all the elements inside that group ZP star. Then and only then we say G is a primitive root or G is a generator of that group. So first and foremost we define P and we define G. Then the function Fa, which is equal to G raised to A mod P, is called the modular exponentiation function with base G and modulus P. So this particular operation you have seen before in the context of RSA. This is relatively straightforward. But the reverse operation, where you're given G and P and now you're given A and you want to find out, so log of P to the base G, its inverse A is equal to log of P to the base G, is called the discrete logarithm problem. So if you're given this number over here, so there's a misprint over here, if you're given this number and you have to find out A, so there are 2 different problems. The exponentiation problem where you're given P and G. In both cases you're given G and P. In the first case you're given A and you need to find this entire thing. In the second case, once again you're given G and P, but you're given this thing and you need to find out A. So this problem is referred to as the discrete log problem, and this is infeasible if you choose the group and the generator appropriately. So I'll just repeat again. You are given the prime number P, and so you're given the group ZP star with operation multiplication modulo P. So you're given that and you're able to find a generator. How exactly we won't discuss over here, but you're able to find a generator of that group ZP star. Then furthermore, if you're given A and you're asked to find out G raised to A mod P, then this operation is referred to as modular exponentiation, and it is relatively straightforward using tricks like square and multiply. On the other hand, if you were given this thing itself, so the inverse, that is log of f of A, this is not P, this is log of f of A modulo P. So this reverse operation where you're given P and G and this thing and you're asked to find A is a difficult problem, and that is referred to as the discrete log problem. So some examples of this, I'm taking a set Z29 star, it's got 28 elements as you can see, 2 raised to 1, 2 raised to 2 and so on, and that is 2 raised to 28 out there. I hope it's visible. So you take 2 raised to 1, that is 2, 2 raised to 2 is 4, 8 and so on, and you find that this number 2 is a generator because it generates all the elements in that group Z29 star, all the 28 elements. So you won't find a repeat out here as you go along. The first one is 2, 4, 8, 16, 3, 6, 12, 24 and so on. All the elements between 1 and 28 will be encountered as we go along this circle. Now suppose you are given the number, say for example you are given the number, this is 2 raised to 1, 2, 3, 4, 5. You are given the number 5, it's easy to compute 2 raised to 5 modulo 29. But suppose you are given a number 9, then to compute this in general is infeasible. So if you are given the number 9, to compute the number x, so that 2 raised to x is equal to 9 modulo 29, that is a difficult problem which is called the discrete log problem. Especially when, so for a small set of numbers, like in this case it's easy, but when this number gets to be very large, then this problem becomes infeasible. So the discrete log problem becomes infeasible in that case, and when I say this number is large, I mean that you require something like 1000 bits to represent that number. So it's something of the order of 2 raised to 1000. So one example which is less trivial, let's suppose we've got the prime number 131. So Z131 star is the group with the operation multiplication modulo 131, and this happens to be a generator. It's not always that G equals 2 is a generator. So it turns out in this case that 2 is a generator. Then you can actually compute this by using a little program. The discrete logarithm of 72 to the base 2 modulo 131 is actually 17, and the reason this is true is that 2 raised to 17 modulo 131 is 72. So if you were given 17, then to compute this is straightforward. But if you are given 72, in general to compute this would be much less straightforward. So this is the discrete log problem, and this is modular exponentiation. So with that brief background to the discrete log problem, let's look at some of the applications. The first application, which most of you are familiar with, is Diffie-Hellman key exchange. Then there's also Diffie-Hellman authentication, and we'll also try to cover in this session Elgamal encryption and Elgamal signatures. So once again, most of you are familiar with this. This was an algorithm, or actually a protocol, the Diffie-Hellman key exchange protocol, that came up in the year 1976 by these two gentlemen, Diffie and Hellman. The problem is the two sides need to exchange a key securely. So they need to come up with a common session key. Assume they've already agreed on a P and a G. If they've not agreed, then A can decide on it and just send it to B. So let's just see how this would work then. So let's look at a picture. You've got A here and you've got B over here. So what A does is it chooses an appropriate prime number P, a very large number, thousands of bits long, and a generator for that group. And then she also chooses an ephemeral secret. So this is her ephemeral secret A, which she sends across. So she doesn't actually send A, she computes G raised to A mod P and sends it across. So that A is like a private key and G raised to A mod P is like a public key. So she sends across the parameters P, G and her public key G raised to A mod P, and the other party B, what he does is he correspondingly chooses an integer B between 0 and P minus 1 and then computes G raised to B mod P and sends that thing across. So G raised to B mod P is sent across, and then when she receives his public key, she computes G raised to B mod P to the power of her private key A, this whole thing modulo P, and the result that she gets is G raised to AB mod P. And what he does is when he gets her public key G raised to A mod P, he raises that to the power of his private key B, so he gets the same value G raised to AB mod P, and nobody knows this value except the two of them. So this becomes the common session key that they will use to encrypt all the messages between them for the duration of this session. So why does Diffie-Hellman key exchange work? So a simple bit of algebra over here. Let's see what she computes. She's got his public key, which is G raised to B mod A. So once again, his private key, which he just chose and didn't tell anyone about, is B, and he computed his public key G raised to B mod P and sent it to her. And then when she gets it, she raises it to the power of her secret, her private key. So this is the computation she performs. She takes his public key and raises it to the power of her secret, and she gets G raised to AB mod P. And this is exactly the same thing as the public key that she gave B, and B took it and raised it to the power of his secret. So now both sides get the same value, G raised to AB mod P. So here's a little example which you can try offline. I've taken P equals 131 and generated 2, and let the secret that she chooses be the value 24. So her public key becomes 2 raised to 24 mod 131, which is 46. So she sends 46 to him, and he chooses 17 as his secret, computes 2 raised to 17 mod 131, which is 72, and he sends this to her. And after receiving B's partial key, she computes the value 72, the value that she got from him, raised to her private key, which is 24, which she chose or generated in this step. So she computes this value mod 131, which is 13. This is the secret that she comes up with, and he comes up with exactly the same secret because he takes the value received from her, which is 46, the value that she gave him, and he takes it and raises that value to his private key 17, which he generated in this step. So 46 raised to 17 mod 131 is 13. Both sides have agreed on a common secret, which they will use to encrypt all messages between them for the duration of this session. So let's look at a possible attack on the Diffie-Hellman key exchange protocol. So choose A as before, and she computes g raised to a mod p. She sends the parameters p, g, the prime number, the generator, and g raised to a mod p across to him. Now there's a man in the middle attack over here. The attacker stands in the middle. Notice what he's doing. He captures the entire message. There's an active attack, not just a passive attack. He captures the message and replaces g raised to a mod p with his own g raised to c mod p. So he chooses a c, he computes g raised to c mod p, and he replaces g raised to a mod p with g raised to c mod p, and he sends the same thing across to him. He innocently does what A did, chooses a b, computes g raised to b mod p and sends it across. Once again, the attacker is in action. He intercepts that g raised to b mod p and replaces it with g raised to c mod p. So what happens is, she thinks that the g raised to c mod p came from B, but actually what B intended to send was g raised to b mod p, and that was modified by the attacker and replaced by g raised to c mod p. So she takes g raised to c mod p and raises it to the power of her private key, so she gets g raised to a c mod p. And he does exactly the same thing at that end. He computes his secret as g raised to bc mod p. So the secrets that this one and this one have computed are completely different. So guess what happens after this? Now every single message goes from her to him, but it again is intercepted by this guy. So what he does is, he gets the message. Now this is encrypted with the key that he knows, which is g raised to ac mod p. This is g raised to ac mod p, and he has also computed the same value, because he has taken the g raised to a mod p that she sent and raised it to the power of his secret, c. So he gets g raised to ac mod p, and every single message that is encrypted with that key, he intercepts, he decrypts, he reads it, and re-encrypt, maybe modifies it, and re-encrypts it with the key that he shares between him and B, which is g raised to bc mod p. So re-encrypts it and sends it across. So it's a very active attack, because he's doing a lot of work intercepting, decrypting, modifying, and re-encrypting and sending it back. The same thing when he receives something from him, and so on and so forth. So this is a standard man in the middle attack. So one question is, what can we do about this attack? How can we prevent this attack? So the way to prevent this is to authenticate whatever parameters are being sent. So perhaps digitally sign all the parameters that are being sent by A and the parameters being sent by B. All of this message needs to be digitally signed by A so that B can verify it. Whatever is B is sending should be digitally signed by B so that A can verify it. Then the man in the middle attack will not be possible. So that kind of scheme is known as authenticated Diffie-Hellman key exchange. Okay, so from key exchange to authentication. So we can use this idea of the discrete log to actually do encryption. So once again, you have a large prime P and a generator in this group ZP star with operation multiplication modulo P. Now what is the private key in this case, and what is the public key? So an Elgamal private key is an integer A. So choose some random integer A between 1 and P minus 1. Once again, the value of P is a very, very large integer which requires about 1000 bits, for example, to represent. It's a very large integer which occupies 1000 bits. At least 1000, could be thousands. So that's her private key that she chooses. The corresponding public key is a triplet where you've got the parameters, the prime number, the generator, and alpha, where alpha is obtained from g raised to a mod p. So this is the public key of this person with corresponding private key A. Now let's see how encryption would work. Elgamal encryption, where we make use of this idea of the discrete log. So once again, P, G, and alpha is the public key of A, this triplet. To encrypt a message M to be sent to A, so B wants to send this message encrypted with her public key. He wants to send it to her. So what he does is he chooses a random number R lying between 1 and P minus 1. For security reasons, that number has to be relatively prime to P minus 1. You can show that if you don't have this condition satisfied, there could be a security lapse. And then B computes two integers. Very interesting. The ciphertext is now two integers, not just one integer as an RSA. The first integer is g raised to r mod p. And the second integer is, it has to obviously use the public key of A. So B uses alpha from A's public key. So this whole thing is given by A to B, possibly in the form of a certificate, and B pulls out the alpha, uses it over here. So he has generated this random number R. He uses the same random number R, and as an index, he chooses alpha from her public key. So alpha to the power of R, multiplies it by his message, and then reduces it modulo P, and that is the second constituent of the ciphertext. So the first one is C1 and the second one is C2. B sends the ciphertext C1, C2 to A. Now the interesting question is, how would you decrypt this? So actually it's very straightforward. Something tells you that to decrypt it, you need to use the private key. So A will have to use her private key, which is little a. So to decrypt the ciphertext C1, C2, A uses a private key little a and computes. So the first part of the message was, if you recall, g raised to r. So g raised to r now to the power of minus a, a private key, and then multiplied by C2, the second part of the ciphertext, which was the message multiplied by her public key raised to the power of r. So that is C2. So this is what we state. This operation we state will help to recover the message M. Let's see why this works. C1 to the power of minus a multiplied by C2 mod p. This is nothing else but g raised to r mod p raised to the power of minus a. That is this stuff. And the second thing is nothing else but what he computed, which is m times alpha raised to r mod p. So this thing is g raised to minus ar. If you use the laws of modulo arithmetic, g raised to minus ar, and then this thing is alpha, don't forget, is g raised to a. So I'm just substituting g raised to a and then raising it to the power of r. So I get g raised to ar, and then this m is over here. Now g raised to minus ar, g raised to ar cancel out, and I just get m mod p, and that is the original message m. So this is how decryption works in case of the Elgamal system. So there are some questions. Is Elgamal secure? So what is one possible way? So now you can think of some very smart ways of recovering the private key or the message from the ciphertext. So one idea that comes to mind is, I know that C2 is equal to m times alpha to the power of r. C2 was m times alpha to the power of r. So what I do is I just write it down as, I just put m on the other side, and I get m is equal to C2 to the power of alpha raised to the power of minus r. And how do I get r? I know that r is related to C1. So these two things are part of the ciphertext. So I know that C1 is g raised to r mod p, and I solve the discrete log problem and I try to recover r. Once I recover r, I use it over here. I know C2, I know her public key, and now I've recovered r from this. So I do this operation and I get the message M. So this is what the hacker thinks. Where is the hacker wrong? The hacker thinks he can just obtain M using this, solving the discrete log problem. But that's precisely what we've said from the beginning. The discrete log problem is very hard. It's very infeasible if you choose the appropriate large group. So in that appropriate large group, it's virtually impossible to solve the discrete log problem. If I know this, I know this, and I know this, it's impossible to get R. R is the discrete log of C1 to the base G modulo P. That problem is impossible. So it was impossible for me to get R. How can I compute this and get back the key? So the hacker cannot get M. Only the person with knowledge of the private key little a can obtain the value of M, as shown before in the previous slide. We were talking about Elgamal encryption, and we were trying to hack into the scheme, and we found that one hack involved computing the discrete log, which is infeasible. Let's consider a second hack, which is based on the vulnerability over here is the way this protocol is implemented. If you use the same random number repeatedly, then there is a chance of being able to obtain the ciphertext. Let us see why. So these are the two equations we wrote down. Now suppose I use the same random number twice. So I have two different messages, M and M prime, and now I've got two pairs of ciphertext, C1 prime and C2 prime. So let us see the things that I know. I know what is P, I know what is G, and I can see the ciphertext. Now let's suppose I know that this is equal to this. So the software that does the encryption has used the same random number twice. So even though the messages are different, so this value C2 is different from this value C2 prime, this message M is different from M prime, however C1 is the same as C1 prime. That probably suggests that they are using the same random number. Now I know what is C2 and C2 prime, and I would like to find out as a hacker what is the value of M prime. Let us suppose the hypothetical case where I also know M. Such an attack is known as a known plaintext attack. Where I happen to know one or more message ciphertext pairs. So let's suppose I happen to know the value of M. The question is it possible to know the value of M prime? On the assumption that the software is buggy and uses the same random number repeatedly. So now I'm trying to find out M prime, given that I know C2 and given that the random number that was chosen for both the encryptions is the same. So if I look at this equation, C2 is equal to M times alpha to the power of R mod P, and this alpha raised to the power of R is the same thing. So I can write down from here alpha raised to R is equal to C2 M inverse mod P. And this is the same thing as looking at this thing, alpha raised to R is C2 prime M prime inverse. Now if you look at these two equations, we know this, we know this, and we know this. Therefore I can find out M prime inverse and I can find out M prime. So M prime is equal to C2 prime times C2 inverse times M. So this is the attack. Knowing the ciphertexts, which I always know, so I can always tap into the line and find the values of the ciphertexts. The thing is, I want to find out what is this message M prime that the victim has just encrypted and sent. I'm assuming a known plaintext attack where I happen to know the value of M for this encryption. So now from this equation I get alpha raised to R is equal to C2 times M inverse, and from this equation alpha raised to R is equal to C2 prime times M prime inverse. So I equate these two and I'm able to solve for M. So for M prime is equal to C2 prime times C2 inverse times M. So the moral of the story is don't repeat the same random number twice. Recall once again that I use a random number in computing the ciphertext. C1 is equal to G raised to R. I'm talking about this R. G raised to R, and C2 is equal to M to the power of the public key to the power of R. Don't repeat this random number twice in two different encryptions. So this is in words what I just explained on the sheet of paper. And this is a simple example. Let P be 131 and the generator be 2. Just choose a private key. A chooses a private key. A equals 97. A public key is 2 raised to 97 mod 131, which is 14. Let the message to be sent be 75. Now the sender chooses a random number, let's say it's 33, and then he does exactly those computations. G raised to R, so 2 raised to 33, mod 131, which is 103, and this thing, M is 75, alpha is 14, and the random number is the same thing over here, 33. and this is 51. So the ciphertext corresponding to the message 75 is two numbers, 103 and 51. So Elgamal encryption actually doubles the amount of space for the ciphertext. And then we simply perform this thing algebraically, C1 to the power of minus A. So in order to decrypt, the private key is necessary. So the private key is 97. So 103 to the power of minus 97 multiplied by 51 mod 131, and the answer is 75. So you recover the original message. Okay, and the final thing about the discrete log, can we use it to actually perform, to generate and to verify signatures? So how do we do that? Once again, let A be the private key of this person A, and let her public key be the different parameters, prime number, the generator, and alpha, where alpha is equal to g raised to A mod P. To sign a message M, she does the following. She computes the hash of the message, h of m. We talked about the cryptographic hash yesterday. So she computes h of m. Then once again she chooses a random number r, such that r is relatively prime to p minus 1. She computes x is equal to g raised to r mod p, just like in the case of encryption. The case of signatures too, this thing is computed, the first part of the signature. And the second number, she computes y as the hash of the message minus, she takes her private key A, multiplies it by this component of the signature, performs this, and then multiplies that by the inverse of the random number mod of p minus 1. So note this over here, it's not p but it's p minus 1. And now the signature is the pair x and y. Now the question is, so this is signature generation. Notice that she has used her private key. Anytime you sign, you have to use your private key. So she's used her private key, and then to verify it, the verifier will use the corresponding public key. So x and y were the two components of the message. What the other guy, that is B, does is he takes the x, raises it to the power of y, then takes her public key, raises it to the power of x. So x and y are the two components of the signature, and reduces this modulo p, and then verifies whether this thing is the same as g to the power of the hash of the message. And you can try and do it on your own, otherwise see section 8.3.2 of the text for proof of why this verification equation holds. So what does he have to do? I want to make sure that this is really the signature of A on this document M. The document is M, the message is M. What I should do is I should compute, the receiver or the verifier must compute h of m, raise g to the power of h of m, and see whether this thing mod p is the same thing as the two components of the signature, pull them out, x raised to the power of y multiplied by her public key alpha, which is typically contained in a certificate, to the power of x, and see whether this thing reduced modulo p is the same thing as this thing reduced modulo p. If it is the case, then we say that the signature has been verified, it's an authentic signature. So with this, I will end the discussion of the discrete log. There were some questions that had come from the remote sites. I will also try to answer them. Maybe I can do some of them right away. So one question was about, I've used the notation Z7 and then Z7 star. What is the difference between these two things, and how many elements are there in Z7 and Z7 star? So usually this notation Z7 really refers to the set of elements. So there are 7 elements in this. Z7 star doesn't include the 0. So it's got only 6 elements. So I just want to point out that this thing is a special case of Z. This thing need not always be prime. I mean, I can consider, for a group, I can consider an arbitrary number n here, arbitrary integer n, but then I have to use the correct definition. The definition of this thing is all the integers x lying between 1 and n minus 1, such that GCD of x and n is equal to 1. As an example of this, I can define Z8 star, and Z8 star with the operation multiplication modulo 8 is also a group. So this thing will be 1. I can't put 2 over there because it has to be, the GCD has to be 1. So choose all the numbers between 1 and 7 that are relatively prime to 8. So 2 is not relatively prime, 3 is, 4 is not, 5 is, 6 is not, 7 is. So these are the elements 1, 3, 5 and 7. So this also forms a group. It doesn't have to be prime. But if I put a prime number, then the elements of that set will be everything from 1 to p minus 1. Well, here you will be skipping some of the elements. So how many elements in Z7 star? The answer is 6. How many elements in Z7? The answer is 7. How many elements in Z8? The answer is 8 elements. How many elements in Z8 star? Answer is 4. In fact, when we considered RSA, when we talked about RSA, Zn star, where n is the modulus, which is the product p multiplied by q, Zn star is precisely, the cardinality of this set is precisely this thing, phi or phi of n, which is p minus 1 times q minus 1. In this special case, the n is the product of 2 primes. Okay, there was another question about the multiplicative inverse in the set Z7 star. I made a mistake as I was writing, so I'll just clarify that. The inverses. So this is not there. The inverse of 1, the inverse of 2, 2 multiplied by 4 is 1. It is actually 8, but reduced modulo 7, it's 1. Likewise, the inverse of 4 is 2. They have to be inverses of each other. The inverse of 3, is it 3? No. Is it 5? Yes. 3 5s are 15, which is 1 modulo 7. Likewise, here 3. And by mistake, I put 1 over here. 6 multiplied by what gives me 1? 6 multiplied by 6 is 36, which is 1. So the inverse of 6 is not 1, but it's 6. The inverse of 1 is 1. Okay, then there was another question. This is from